Welcome to the course Design of Reinforced Concrete Structures. In today's lecture, let us solve a problem on development length. So, the question given here is an RCC beam 250 mm by 500 mm has a clear span of 5.5 meters. So, here an RCC beam is given and the cross-sectional dimensions and the clear span of an RCC beam is given. The beam has 220 mm dia bars going into the support. So what the RCC beam has how many bars? 2 bars and the dia of the bar is 20 mm and those bars are going into the support. The factored shear force is 140 kilonewton. So the factored shear force is how much? It is given, it is 140 kilonewton. Check for the development length if Fe 415 and M20 grade of concrete is used. So here what is asking to check? Is asking to find out or check for the development length. If the grade of steel is Fe 415 and the grade of concrete is M20. So first let us write down the given data. So what is the given data here? The breadth of the beam is given. How much is the breadth of the beam? It is 250 mm. And the depth of the beam is given. So what is the depth of the beam? The depth of the beam is 500 mm. And the clear span is given. So what is the clear span given here? The clear span is 5.5 meters. And the number of bars are given here. How many number of bars we have? 2 bars of 20 mm diameter. So from this what we can find out? We can find out the area of steel, which is nothing but the area of steel. Now the shear force, that is the factored shear force is given. That is V is given here. How much it is? 140 kilonewton. So here directly the factored shear force is given. If only shear force is given, then you have to find out the factored shear force by multiplying it with a suitable partial safety factor. So here directly the factored shear force itself is given, which is 150 kilonewton. And what is the grade of steel? The grade of steel is Fe 415. That is Fi is given as 415 Newton per mm square. Given the grade of concrete is FCK is equal to 20 Newton per mm square. So these are the given data. God is asking to check for, he is asking to check for the development. So if you observe here, what are the details which are lacking? We have to know the D, that is nothing but the effective depth, and the area of the steel has to be known. We have to calculate the moment, we have to calculate the bond stress tau BD. All these things has to be calculated. So first let us calculate the effective depth D. So effective depth D. So how can we calculate the effective depth D? Effective depth D is equal to the overall depth minus clear cover minus diameter of bar divided by 2. So the overall depth of the beam is already given. How much is the overall depth? It is 500 mm. So D is equal to 500 minus clear cover. So here I am assuming a suitable clear cover. So I am assuming a clear cover of 20 mm. So the the case cover is how much it is? 20 mm minus the diameter of the bar. So what is the diameter of the bar given in the question? It is 20 mm. So 20 divided by 2. So if you solve this, you will get a value of 470 mm. So what is the effective depth? We are going to consider here. The effective depth D is 470 mm. Now we have known the effective depth D. So what is the next unknown we have to calculate here? We have to find out the area of steel, which is AST. So now let us calculate the area of steel. So how will we calculate the area of steel? Area of steel reinforcement. AST. So what is the formula? It is N into pi d square by 4. So what is N here? N is nothing but the number of bars. How many number of bars you have here? 2 number of bars into pi into d. D is nothing but the diameter of the bar. So what is the diameter of the bar here? It is 20. 20 whole square divided by 4. So if you solve this, you will get a value of 628 mm square. So what is the value of AST? AST is 628 mm square. Now we have calculated the effective depth D and have calculated the area of steel AST, which is 628 mm. So in the check for the development length, what is the first step what we have to do? We have to calculate the moment. Okay, that is we have to calculate the moment M1 at that particular section. Now let us calculate the moment of resistance at that section. So the moment of resistance M1 at that section. So what is the equation for calculating the moment of resistance? It is M1 is equal to 0.87 Fy into AST into D minus 0.42 XU. So the value of Fy is already known, which is 415 Newton per mm square. AST we have calculated, it is 628 mm square. D also we have calculated, which is nothing but the effective depth, which is 470 mm, and XU. So here in place of XU, what you have to substitute? You have to substitute XU is equal to 0.87 Fy into AST divided by 0.36 FCK into this has to be substituted here. So substitute Fy, the value is known, AST is known, FCK is known, and B also known. So substitute all these values in this particular equation so that we will get the value of M1. So let us substitute the values. So it is 0.87 into Fy. Fy is how much? 415 into AST. AST is 628 into D. D is how much it is? 470 minus 0.42 into XU. XU is 0.87 into Fy. How much is Fy? It is 415 into AST. How much is AST? It is 628 divided by 0.36 into FCK. How much is FCK? It is 20 into B. How much is B here? B here is 250. So if you solve this, we will get a value of M1 as 94.748 into 10 to the power of 6 Newton. So this is going to be a moment of resistance m1 at that section. Now what? We have calculated the moment of resistance m1. So in the development length, what is the next step? What we have to do? We have to calculate the development length, LD. So how the development length is denoted? It is denoted by LD. So now what we have to calculate? We have to calculate the development length LD. So let us calculate development length LD. So how you can calculate LD? LD can be calculated by using the equation which is given in clause 26.2.1 of IS 456-2000. So in clause 26.2.1 of IS 456-2000, the formula for calculating the development length is given. So by using that, let us calculate the development length. So what is the formula? LD is equal to 0.87 Fy into 5, that is the diameter, divided by 4 into tau BD. Okay, so tau BD here is nothing but the bond stress, Fy is the grade of steel, and phi is the dia of the bar. So now what? Fy is already known. So Fy is 415 Newton per mm square, and phi is already known, that is the dia of the bar. So but the unknown here is what? The unknown here is tau BD, that is the bond stress. So what we have to calculate first? We have to calculate the bond stress. So how will we calculate tau BD? So the tau BD can be calculated by using the table which is given in clause 26.2.1.1 of IS 456-2000. So in IS 456-2000, if you check clause 26.2.1.1, there will be a table, and from that table you have to find out the tau BD values. So the tau BD values are given for different grades of concrete. So in that particular table, for the grade of concrete 20 Newton per mm square, the tau BD value is given as 1.2 Newton per mm square. So the tau BD value is given as what? 1.2 Newton per mm square. But that particular tau BD value is valid for plain bars. That is for Fe 250 bars only, the tau BD value of 1.2 Newton per mm square is valid. Here, what is the grade of steel we are using? The grade of steel is 415 Newton per mm square. That is, we are using the HYSD bars here. So if we are using the HYSD bars, below this clause there is a point. In that particular point, it is mentioned that for HYSD bars, there should be an 60% increase, okay, of the bond stress. That is, for this particular value, you should increase up to 60%. Okay. So based on that, let us calculate the tau BD value. So 60% in the sense is what? 1.6 into this value for the grade of concrete 20. That is 1.2, which will give you 1.92 Newton per mm square. Okay. So the tau BD value, how much we have got here? We got it as 1.92 Newton per mm square. So if you substitute the tau BD value in this particular equation, we can find out the development length, which is nothing but the LD. Now substitute all the values and find. Now let us calculate the development length LD. LD is equal to 0.87 Fy into 5 divided by 4 into tau BD. So substitute all the values. It is 0.87 into Fy is the grade of steel, which is 415, into 5. 5 is nothing but the dia of the bar, which is 20 divided by 4 into tau BD. Tau BD value we have calculated right now, which is 1.92 Newton per mm square. So if you solve this, you will get the value of LD, which is 940.2 mm. So now we have calculated the development length, that is the value is 940.2 mm. But now what he is asking here, he is asking to check for the development length. So the check for the development length is, the development length LD, it should not exceed, okay, the LD, okay, should not exceed m1 by v plus L0, okay, where m1 is nothing but the moment of resistance at that particular section, v is nothing but the shear force, and L0 is nothing but the anchorage length. Okay, so that is, what does this mean? The code has suggested that the value of this should be always greater than LD value. That is, the LD value, it should not exceed this value. So now let us check for the development length. So to check for the development length, what we have already calculated LD. Now we have to calculate this, that is m1 by v plus L0. So m1 is nothing but moment of resistance, which we have already calculated and we have got a value, and v is nothing but the factored shear force, which is already given in the question, which is 140 kilonewton. And what is the unknown here? The unknown here is L0. L0 here is nothing but the anchorage length. So first let us find out the anchorage length. So this particular formula is given in clause 26.2.3.3, okay, of IS 456/2000. So this you can see in clause 26.2.3.3 of IS 456/2000. Now what? We have to find out the L0, that is the anchorage length. So what I am doing here is, I am providing a 90-degree bend at the center of support. So at the center of support, what I am providing a 90-degree bend. So from this, I will find out the anchorage length L1. So if I am providing a 90-degree bend at the center of the support, how will calculate the L0? L0 can be calculated by 8 phi. So why 8 phi? For every 45 degrees, okay, of bend, okay, the anchorage length can be calculated by 4 times the diameter. So as here it is 90 degrees bend, so 4 into 2, because for 45 degrees it is 4 phi, for 90 degrees it will be 8 phi. So anchorage length can be calculated by 8 phi. Phi is nothing but the diameter of the bar. So 8 into phi is how much? 20, which gives you 160 mm. So here our anchorage length is going to be 160 mm. Now find out m1 by v plus L0. So m1 is already known. How much it is? It is 94.748 into 10 to the power of 6 divided by v. V is nothing but the shear force, which is 140 kilonewtons. I am converting it into newtons, which will be 140 into 10 cube plus L0. We have got the value, which is 160 mm. So if you calculate this, you will get a value of mm. We get a value of 836.77 mm. So what is checked for development length? That is the development length LD. It should not exceed this particular value. So how much we have got the development length? Development length we have got 940.22 mm. So the value of LD is how much? It is 940.22 mm. And this value how much we have got? 836.77 mm. What is happening here? So the LD should not exceed this, but here it is more than this. So it is not meeting the codal requirements. As this particular values are not meeting the codal requirements, I have to increase the anchorage length. So now what we'll do is we will increase the anchorage length. Now what? The codal requirements are not satisfied. So for that reason what I am doing here, we are going to increase the anchorage length. So here what I am doing, I am providing a U-bend at the end support. At the end of the support I am going to provide what? I am going to provide a U-bend. So for a U-bend, what will be the anchorage length L0? L0 will be 65. So the anchorage length L0 is equal to 65. So 16 into 5 is nothing but the dia of the bar, which is 20. So which will give you 320. So what is the anchorage length here? Now I have increased the anchorage length. That is L0 is 320 mm. So again calculate M1 by V plus L0. So M1 is how much? It is 94.748 into 10 to the power of 6 divided by B is 140 into 10 cube plus 320 mm. If you solve this, you will get a value of 997 mm. So what? The check for development length is what? This particular LD value, it should not exceed this value. That is, LD should be less than this value. So if you observe here what? LD is less than this particular value. So now we have satisfied the codal requirements. So hence the development length is okay. That is the check for the development length is okay. Why? Because here 997 mm is greater than 940.2 mm. So the codal requirements are satisfied. The codal requirements are satisfied. So this is how we have to check for the